University of Massachusetts at Amherst, Chemical Engineering, Polymer Science 757, Polymer Rheology, H.H. Winter, Lecture 25A. The rheology of block copolymers is very interesting because of the morphology those materials develop. And I want to show a few examples of of measurements on block copolymers. Let me first introduce in general what we mean with block copolymers. Chemists are able to link immiscible blocks, that would be one block, with another immiscible block, and they would naturally not mix on a molecular level, but since they are tied with a chemical bond, they cannot separate beyond molecular level. So we will get phase morphology on the 100 angstrom level, on the radius of gyration level of those molecules. The diblock has the most simple geometry, but you can have a triblock, say block A, and another block A connected with a center block B, or one could have multi-blocks alternating, or in some statistical sequence, the statistical sequence would give long sequences of one species mixed with short sequences and everything in between. One can get star molecules, which again would be fairly regular, having a center region dominated by chemistry A and the arms by chemistry B. The molecules up here, the diblock and the triblock of this type, form some highly ordered microstructure. They are self-organizing, one says. The multi-block are not as ordered, and we won't talk about this today, but they form interesting thermoplastic elastomers, interesting network materials also. The stars can also form very ordered regions. The joining of those two immiscible blocks thermodynamically leads to some phase separation effects driven by the enthalpy. When the blocks are separate, somehow energetically we have a lower internal energy, so that's favored energetically. However, the motion of the molecules is somewhat hindered by a link in between the molecules, so we are sacrificing entropy. And for the internal energy, there's a balance between the entropic effect and the enthalpic effect of those block copolymeric molecules. If the energy, the internal energy gives a phase-separated domain structure, then we would be interested in the specific geometry and the size of those phase-separated regions. On a small scale, so on a molecular scale, those systems form ordered regions. So this is on 100 angstrom scale or 10 angstrom scale. If you have the phase separation in action, if you go beyond the coexistence temperature, it's a miscible system, and those chains are just interpenetrating each other on a molecular scale. This would be one phase. On a 100 angstrom scale and above, these phase-separated regions order, in some cases in form of a center cubic spheric morphology, or we would have cylinders on a hexagonal lattice here, regular structure, or at intermediate morphology, they form the material forms lamellae of AB alternating. There's also a special case which occurs for diblocks where double diamond structure is interpenetrating. Now, all of those geometries depend basically on the geometry. They depend on the volume fraction of the components. At a low volume fraction A in a matrix of B, you get spheres, intermediate volume fraction cylinders, and at 40 to 50 volume percent, you get this lamellar structure. On an even larger scale now, those ordered regions seem to form in a nucleation and growth mechanism when you get them from solution. So there's one region may be ordered and it's growing and forming a grain, and there are other regions having an initial order which is different and also forming a grain, the boundaries are discontinuous, but within a grain, the order is fairly homogeneous. The fluctuations might be very, very, very small. In rheology, we see phenomena on all length scales. You will see on higher frequencies, you will see molecular, the chains, and then going to lower frequencies, longer times, you see the phase-separated structure. And beyond that, you see the regularity of those domains. And you might even pick up grains if you go to very, very low frequencies. So with a mechanical spectroscopy, we can scan all of those. On a molecular scale, these systems are fairly disordered. Except for the vicinity of the interface, the chains are pretty much coiled. So they are disordered, they are isotropic. The anisotropy, or the order, comes only through a large-scale self-organization. So within this domain, there's disorder. The molecular chains are really randomly coiled. So in the next, the rest of this lecture, when we talk about order, we talk about the domain order, not the molecular order in that system. A phase separation, the transition from this morphology to that morphology has been observed rheologically by Bates, for instance. In '84, he published a very nice paper where he had typical liquid behavior in the one-phase region, and then when he lowered the temperature at about 180 degrees C, he phase separated his system and obtained long slowing down of the molecular mobility, and that's been seen in this part. At high frequencies, no change is seen. So the phase separation and the overall ordering, the large-scale ordering, is found at low frequencies, at long times, and that's where we would expect the phenomenon. It's very, very small at those high frequencies. This was at diblocks, but at triblocks you also find the same phenomenon. This is Faith Morrison's experiment on a styrene isoprene styrene system with 65,000 molecular weight. And there, again, the liquid-solid transition occurs at can be seen at low frequencies. The slope is different here. It's close to 0.4, while in Bates' experiments, the slope was close to 0.5. And here, the transition temperature is near 180 degrees. So that can be seen in many, many different systems. It was already found in 1977 by some experiments of Potter and Greenlock, where the viscosity, now he didn't look at the spectrum, where the viscosity drastically increased as the system phase separated, or Chang and Lin found the same thing at a similar system where, again, a phase separation increased the viscosity at low rates, or the spectrum here. See, that's very similar to Bates' observation. The spectrum goes from a liquid-like to power law type spectrum. We were interested in power law spectra in connection with gels, the gel transition. So the formation of the order is reducing molecular mobility. So we are producing a network by ordering the material. So in that sense, it's also a solidification process and has a very similar fingerprint as the sol-gel transition in liquids. Now, this was already in '78. So it has been found in many, many laboratories, very established fact. In the following, I will pick a very specific material and show a few phenomena of this self-organization and ordering and flow. How can we change the material by subjecting it to deformation? This is a commercial material from Shell, which is fairly uniform in its composition. It might contain some diblocks, maybe 10 or 15% diblocks. The way those molecules are made is the following. The center block is cut in half, so we have a polybutadiene, which is terminated with a long styrene block, and two of those are then merged to form the polybutadiene chain in the center. This center chain is very long. It's highly entangled. The styrene blocks at the outside are of very low molecular weight. They're probably randomly coiled. They relax very quickly to everything we will do when subjecting that system to flow. They always will reorganize very, very quickly. The center block is entangled and will show very long relaxation times, and I'm sure that has a large effect on the phenomena which we are seeing. The polystyrene content is 26%, and that's typical. That's somewhat in the middle of the region where you get cylinders, cylindrical styrene domains in a continuous polybutadiene matrix. The Tg of polystyrene is high, so we have those cylinders which are glassy at room temperature, and the matrix is very, very mobile. If it wouldn't be for the styrene end blocks, it would be flowing, but this way they are locked in and we're forming a thermoplastic elastomer, and this is the chi-n value which characterizes the phase separation of that system. Technically, you could combine many, many different systems. You could have a discrete phase, the cylinders or the spheres, being glassy, rubbery, or crystalline, and then you could combine it with any of glassy, crystalline, rubbery phase, and then get all kinds of morphologies. For the thermoplastic elastomers, we are looking for a glassy discrete phase in a rubbery matrix, and that's the example we are looking at. It's this type of material is interesting as a rubber substitute. It can be processed like a thermoplastic elastomer at high temperature. You deform it like a regular melt, but you don't have to cross-link it. You also can recycle the material. You can reuse it, while a rubber which has been cross-linked in a tire is very hard to recycle. You have to break it down in its monomer units. Exciting is the structuring of those materials, the self-organization into cylindrical domains. That's actually why I picked that material. I thought it's more interesting to look at cylinders than looking at lamellar structure or spheres. But even the morphology with spheres is fairly regular, and the regularity in the structure, in the sphere structure, if I maybe this regularity here, if you have just a small amount of one component on a regular spacing here, on a regular lattice, that small amount hinders the motion of the molecules, and it has a large effect. It's not like a filler. It's really an ordered system, and rheology is drastically affected. In somewhat it looks similar to the rheology of the cylinder, the structure with cylinders. It's not as extreme. So in that sense, it's typical what we are seeing with the cylinders. The order in a system like this is not only given by the direction of the cylinders. We would draw maybe a director to describe that order. Later on, we will specify the director for samples or for grains. And it's the order is more detailed. When you look here, there's a hexagonal spacing of those cylinders, so the distance is very regular. They're moving on a hexagon, and the spacing of the distance of those cylinders is connected with the diameter of the cylinders and with the volume fraction of the polystyrene. Here, this is calculated, for instance, for styrene, isoprene styrene of 65,000 molecular weight, and there A is the lattice parameter, D is the diameter, and phi was the volume fraction of polystyrene. So we not only have the director of that system, we have to look at the hexagon, the orientation of the planes in this hexagon, and those can be picked up with small angle X-ray scattering. And we're using the small angle X-ray scattering because of the large scale of that order. If you would look at molecules and maybe a sequence distribution along the backbone of a molecule, you would use wide angle X-ray. But here we have structures in the 100, 200 angstrom level, and there small angle X-ray is appropriate. The setup is something like this: a radiation source, a copper K alpha source is giving us the radiation. There actually should be one pinhole here. It's about 2 millimeters in diameter. There's a second pinhole, and a small beam is impinging on our sample, and then it's scattered, and on the film we're observing the pattern. This distance is 23 centimeters about, so it's about this distance, and that distance is actually very close. It's just 15 centimeters, so the distance is reversed in that drawing. This source should be very close to the sample and pinholes in between. So this is the pattern we are going to look at, and the constructive interference given by Bragg's law is achieved if in our sample, if there are some planes, if there are some regular planes like drawn here, if they are occurring in the sample, then a scattering will occur, and there will be some interference which give the pattern on the film. And that's what we're going to look at. In our case, D is very large. The spacing is very large, maybe 150 angstrom or so. Then a small angle theta will give us this interference. And that's an advantage for making those pictures only if this angle is fairly small. It's maybe half a degree. Then we get interference. If this angle is bigger, that means if we are having 2 planes here, and if they are in an angle with that light beam, if the angle is too big, we will not get an interference pattern. So the pattern on the film will only be there if we get order. If we get order along if we have order in the structure in the direction of that light beam, and that's very nice. If you would have a smaller value here, then you would get some scattering even in larger amounts of larger deviations from here. So you will see the patterns from that structure are very regular because of that spacing. It's just right. Now, when looking at scattering from regular structures, here you see an example, cylinders being on the hexagonal pattern. Okay, now when looking at this type of structures, the crystallography people have a special type of language, and that goes something like this. They specify planes. They give names to planes. In the first step, they choose axis of that structure. In this case, we have our axis A1, our axis A2, and our axis A3. And then they give names to planes. Like this plane here interferes with the first axis at this. Oh, we also have to specify the characteristic length, the lattice parameter. So this lattice parameter would be would be our length scale. This would be distance 1 here out here, one length, lattice length. So this plane interferes with spacing A1 at 1 out here, 1 unit out here. And this plane interferes with our second axis at -1. This is specifying as the second index. And the third index is specified with this plane interfering with A3. That's giving us this index. And actually interference between this plane and that plane will be at infinite distances. And now let me come back to this number. For the third number, the interference is at infinite, and actually it's 1 over the distance where it is interfering. So it's 1 over infinity gives us 0. Here it's 1 over -1, the interference, so we have -1. And here we have +1, the interference, so 1 over +1 gives us this number. You can really, for instance, say this is the intersect with the A1 line to the -1, something like that. And you do this for all 3. Now, the fourth axis is really the axis normal to that structure, and the interference of this plane here with that axis is again in infinity, so 1 over infinity is 0. So that's the fourth index of that structure. So that's how those planes are given names. We will look at the innermost planes. We will look at the refraction of those planes, and we will not look at these planes, which are further away. So there's a lot of interference patterns coming out of a regular structure, and we will concentrate on the innermost reflections of this. The innermost reflection for the structure, which you just saw, in a light beam going down the hexagon, will give us reflections here from this plane, just a reflection up, reflection on below. And from these other planes, you will get accordingly this reflection, and from those planes, you will get this type of reflection. So from this regular structure, you get 6 reflections, and the pattern is just rotated by half that lattice angle. If the structure is rotated, then you can see that in the X-ray again. Now, this structure has to be fairly aligned. If it's tilted too much, you won't see anything. It really, the X-ray beam has to be along that structure. Then you see this. You will recognize the rotation of that structure by looking at the rotation of those patterns. When you look at the hexagon structure from the side, there are only these planes reflecting, and you see those 2 reflections. And if you rotate that, you wouldn't have reflection from the innermost distance. You would have some additional reflections coming in from the outside. Like here, if you would take the outside reflection, you would have the next reflections coming in something like this. But we won't look at those in the film. So those further out reflections you will see. Same thing from when looking at this structure, a light or the X-ray going on this will not give any innermost reflections. But with this here, again, we will pick up those planes, and you will see those reflections. So small angle X-ray gives us an interesting tool to look at the order in the entire sample. We pick up the order from the whole volume, from a larger control volume in that sample. We will use a second technique to look at order in the system. That's TEM. We will cut samples at low temperature, in this case at 110 degrees, and stain the structure, and then look at those morphologies in the electron microscope. But there you only get a 2D picture of the structure, and it will be very local. You will see disruptions of morphology very nicely in TEM. So those 2 techniques we are going to use. The first thing to look at is the regular scattering from a granular structure which has cylindrical morphology. The first peak is that's the peak I was talking about before. This is the first reflection of the innermost planes. But then there are some higher order reflections, and they are marked here with those arrows. They're typical for the hexagonal morphology. This is the disordered sample, just a film cast from a typical sample with cylindrical domain morphology. The cylinders themselves also scatter, and they give a form factor which is drawn here. We give some local minimum which is superimposed. So when looking here, we won't have any interference with the cylinders themselves. You can measure that pattern in circular. Here it's an isotropic sample because the grains are really ordered regularly in all directions. So you're getting really circles in this case. It's the initial sample. S-cast has regular morphology, phase separated, and that's the starting point of things we are going to look at. For instance, we can measure G prime, G double prime, linear viscoelastic behavior of that material. The high frequency behavior here is given with a rubbery plateau. Then there's a long transition if you go to lower frequencies, but it doesn't show really liquid behavior. There is the mobility is reduced because of the phase separation. In spite of the phase separation phenomena, we can apply time temperature superposition over wide temperature ranges. That's why we have the data here plotted over such a wide frequency window. And that was quite surprising, having a phase-separated structure, which doesn't show any significant effect on phase separation. Often changes the shifting coefficient, and then you cannot apply time temperature superposition, and you can use that really as an indicator of a phase transition in the material. So far about the granular material. Let's move to some more interesting phenomena. The randomly ordered, or the grains with random order, or with a random director here, and random hexagon order, can be converted into a single crystal structure. Now, single crystal means that our director is uniform in the sample, and that also the hexagon planes are aligned uniformly through that sample. Even if the director is uniform and the hexagon is rotated from one part to the sample to the other, that would not be a uniform structure. It would generate some interface in where those different orientations meet. So that would be the single crystal structure on a 100 to 300 angstrom level. Molecules are still disordered in that system. Keller and his co-workers produced single crystal, or they termed this structure single crystal, and they found the periodic rearrangement of those segregated microphases. A lot of work coming out of the Bristol groups, but Hasianou in Strasbourg produced simple single crystal structures in a similar fashion. We did this in our lab, and you will see it from many different labs coming. Bates produced some nice single crystal structures. The structuring has been imposed by shearing the sample at very low rates. We wanted to use different techniques which would give us large samples of highly ordered morphology. For that case, we applied planar extension. And that's a deformation where this sample is extended in this direction, held constant in the second direction, and it's shrinking in from the top and the bottom. So we have a mold which has lubricated surfaces on the side and top and bottom, and there we're squishing this sample and making it long. In that squishing, the stretching of that sample produces an ordering of the domain structure, and we will study this ordering using TEM and also using small angle X-ray. This would be the sample after stretching, and we can look at this sample in Z direction sideways, and you find arcing here. The cylinders are ordered. We have a director like this, so we have very, very nice order. And when you look from the top, you also will see aligned cylinders now, and you can see there's more arcing, so the order is not as perfect. Somehow the width of those arcs is a measure of the perfection of the order. And when looking down along here, we will find disorder. That means that the molecules are aligned, or excuse me, that the cylinders are aligned in flow direction, in X direction, but the hexagons are still rotated randomly, and you can see this when looking at the micrograph. There's a rotation here in the hexagon. This is the micrograph, actually looking down in cylinder direction, and you can see that the hexagon planes are not uniform, and this causes interfaces, and that's why the side view of our sample is kind of wavy, because the cylinders are aligned, but we are generating all those interfaces by reorienting the sample. That was at a stretching of 4. The sample of initial length 1 had been stretched to a final length of 4. Now let's take a sample and stretch it to a length of 6. So more stretching. All the stretching is done at 120 degrees at fairly low temperature, just 20 Kelvin above the glass transition temperature of the styrene. Again, we have a nice alignment of the cylinders when we look sideways, if you look edge on or from the top and the bottom. But then when looking down the sample, you see very nice hexagon coming in. So we have a fairly uniform alignment of the hexagon planes. Two observations. The alignment is parallel to the sample, or to the squeezing direction. It's parallel to the sample surface, and you can see this because of the reflection is on the top and on the bottom. And from our initial picture, if I can find that, you can see that this was reflecting a special type of order. And so when the reflections are top and bottom, we have hexagons which are aligned and like this, and the plane of this is parallel to the plane of the sample. We don't know why this occurs, but it's quite an interesting observation that those hexagon planes are aligning. You can see the alignment here, but there's some discontinuities, some grain boundaries which are still present. Here the regions are fairly uniform, but still also a little bit of disruption. But it's a nicely ordered sample. Oh yeah, this was one observation which is interesting. The second observation is that the spacing is not affected by the flow. We deform the sample, the cylinders probably break up and they reform, and the new structure has the same spacing as the previous structure. So that spacing is really determined by phase separation, by thermodynamics, and it's not affected by the flow. And the thermodynamics is so strong that we cannot overcome that by flow. So the spacing is always maintained. The deformation here has been followed by annealing at 120 degrees for 2 hours. We try to introduce some order by flow and then heal any rupture which we produce by the deformation to get the most perfect structure. If we do the same experiment at more stretching, there's say 8 units, you can see that there's already a deterioration of the order, and the director is still aligned. And then if you stretch at even higher stretch ratio, lambda is equal to 10, then you get a randomization, and from the side the structure is pretty much scrambled, and from the top you can see the hexagon planes are fairly disordered. That's really the morphology which is generated in processing. It's not the self-organized system which you produce in some equilibrium thermodynamic experiment where you give time for formation of order. That's the morphology. Here's a larger picture of that type of morphology, and you can see that it's highly disordered. It's hardly, this is down the cylinders here, and it's hard to see any irregularity in the hexagon pattern because the cylinders are so small in this case. In shear, you are able to produce a similar order. Here we have a sample which has been sheared for 30 shear units, actually in a cone and plate device, not in plate and plate as drawn here. And sideways, the order is fairly uniform. Here we get a very nice uniform ordering. And from the front, you can see the hexagon pattern coming in. It's not completely perfect. There's some disorder coming in. We later on actually found that a shear of 12 would give us the best order. And here we overdid it. We sheared further. But the order doesn't break down as quickly as it breaks down in an extensional flow. So gamma of 30 is still OK for producing a kind of OK a sample, uniform morphology. This is the first part of the experiment where we produce a sample of uniform order, and we will probe that sample in a set of different experiments. Maybe we should break here for a moment and then look at the behavior, look at the property of that ordered structure in 2 different types of experiments, and go from there. So this is Chemical Engineering, Polymer Science 757, Lecture 25B. To sum up what we saw so far, shear flow and extension flow are able to produce a single crystal structure. The order is achieved at some intermediate strain. If we exceed that strain, we see the order deteriorating. We're breaking down that order. Basically, the phase-separated morphology is hindering the flow, and the molecular motion which you need for producing a flow will disrupt the morphology, will disrupt the grains, and you will in flow you will have a disruption balanced by a reformation of order in that system. So if we go beyond that, we always will disrupt the order. So here our objective was to form an ordered structure, and we got this by an intermediate stretching to 6 times the initial length, 4 times gave us a random structure, or stretching beyond, say by 8 or 10, will also give us eventually a random structure. So we will stay at 6 and anneal the sample to get a more perfect structure. Larger picture of the structure is given here. The cylinders are fairly uniform, the director is fairly uniform. You can see that also sideways. The hexagon is also fairly uniform in its alignment, but there's still some grain boundaries, some defects which couldn't be avoided. We end up with a sheet which is fairly large, maybe a millimeter in thickness, coming out of this planar extension. And that type of sheet cannot be probed in a rotational rheometer, because there we would expose the sample to a rotation. And if you would cut a rotational sample, the alignment in that sample would be radial in some part and would be tangential in the other part of the rheometer. And so it would not be uniform, and we couldn't analyze our data. And here came Lin's suggestion, where he said we should cut pizza pie-shaped samples. Maybe he was just eating a pizza when he got this idea. So cutting down the sample into those pieces and rearranging them into a pizza-like, where in this case the orientation is sideways and then it's all around. Or in this case, if we cut the pieces like this, the alignment is in radial direction. The angle is 20 degrees. There were 18 pieces taken. So the misalignment, say in this region, due to that type of geometry, is about 6 degrees, a little less than 6 degrees, and that's not very much. It's a pretty uniform alignment, I would say, in this circumferential direction. We couldn't do it in the third direction, so we are just probing the sample in clamping it. So that's a little harder to interpret. But those two geometries we can clearly probe and get very, very nice data. The probing, again, is, as in many cases before the dynamic mechanical experiment, we get G prime, G double prime. However, it is a directional dependence for G prime, G double prime. See, we do a linear viscoelastic experiment, and in the isotropic case, it's enough to measure this modulus, and then you can predict flows of all kinds in all kinds of directions in the general case. But in our case, we measure this modulus when probing the sample parallel, and probably linear superposition holds when doing that, and when probing the sample normal to the cylinder orientation. And again, linear superposition might hold as long as we stay in this type of orientation. But we don't have enough information to formulate a most general modulus for an anisotropic material. So this would be anisotropic material. Before, we always talked about G of an isotropic material, which only needed one function to describe all the rheology. So please keep that in mind when looking at the sample, at the data from the samples. You will see data taken where the shear flow is imposed in the direction of the cylinder, where it's imposed normal to the cylinder, and some information we have where the cylinders are in the two direction in this case. But most information is really on this type. In the solid state, we can probe the material in all three directions, and you can see that the spectrum of the S-cast sample, here you see G double prime and G prime at 60 degrees, so we are really probing the thermoplastic elastomer of a sample which is cut from the ordering here at stretching of 6 and annealing, all this. So this is then the normal, probing normal to that, and somehow the modulus is reduced in this case, in the solid. Parallel, the modulus is somewhat increased, and in the third direction in the solid, there's some further increase. So the mechanical properties of the solid are highly anisotropic, and you have to account for that. But even in the liquid, the phase-separated structure persists into the liquid state, and you can probe now with a cylinder sideways, the cylinders in the three direction, and you can see that the moduli G prime and G double prime are, or G prime is this, G double prime is that they are higher than the moduli in the S-cast sample. And if you probe in the other direction, you will find the counterpart to that, the moduli, are reduced as compared to the S-cast sample. And when you take now, this is just one sample where the moduli are direction dependent, and if you put those on top of each other, you find that the difference between the moduli is nearly an order of magnitude at low frequencies. At high frequencies, there's practically no effect, but at low frequencies, the difference between those two is quite significant. So it's a large effect, and this already tells us something about the flow behavior, what to expect from flow on those structures. Somehow, when the modulus is high, flow will have a bigger effect on that structure and will break it down more rapidly. But it seems that the hexagon structure, when we talk about the hexagons here, if this is the structure from the side, if you're probing the structure like this, the order hinders the motion of the cylinders drastically, and just small displacement of that structure already gives rise to fairly large stresses. While if you're probing the structure up and down along those cylinders, molecules can still move along the domains, along the cylinder domains, and there's some rearrangement possible, and that allows flow to some extent and will keep the stress level fairly low. That's one type of experiment we want to do. We want to see the anisotropy of the mechanical properties of that system. Now let's see how we can change the structure by flow. And in this case, we will not start from a disordered sample. We will start with an ordered sample where the cylinders are uniform throughout the sample. Again, Lin's method is used here, having pizza pie pieces spliced together and healed with some toluene. So we have a sample now where the cylinders are aligned radially, and for a shear flow geometry, that radial alignment means that the cylinders are in three directions of the shear flow. Shear flow is having a one direction flow direction like this, two direction coming out of the sample, and three direction is the neutral direction or vorticity direction. And that's where those cylinders are positioned. And we want to know now, how does the structure go from this initial order to the final order? Again, we will use small angle X-ray scattering to probe the structure at intermediate strains. Now, in this case, the sample will be sheared and rapidly quenched. The shearing will occur at 140 degrees so that we can deform the sample fairly easily, and then quench it to maintain intermediate structures. Due to the high molecular weight of the middle block of the polybutadiene, the global rearrangement of that structure is fairly slow. The rearrangement within the cylindrical domains will be fast because the styrenes are very low molecular weight. but the matrix is of high molecular weight, and we have time to quench any intermediate structure. Actually, we found that we could leave those structures for hours to reorganize the pattern. The rotation of those hexagon patterns might need hours at this temperature. Very, very slow process. So the experiment is like this. We start out with an initial orientation of cylinders in 3 direction, and we end up with the cylinders in 1 direction. So the director is rotated by 90 degrees. We couldn't say that we rotate the cylinders by 90 degrees. We probably break those cylinders and rotate some fractions of those cylinders into the new direction. Then there's some healing has to take place. So it's not like a fiber suspension where a cylinder is taken like this and it's moved into the new direction. Actually, we don't have detailed information about those cylinder orientation. These are the X-ray pictures which I'm going to use to describe the sample. And the technique is something like this. Let me use my glasses to denote how we are going to look at the sample. The standard is something like this. You take an object and you look at it this way and you see the projection down here. And then you take the sample and roll it over to the side and you look at the object this way and you see the projection down here. So you're just rotating the object, and then you take the object and rotate it down like this, and then you project it sideways. So these are the 3 things we are looking at. And in fact, this is our initial sample. Remember, we had cylinders in the 3 directions. So here we are looking at 3 directions. Our coordinate system for this observation is something like this. We have our 1 direction. We have our 2 direction. This is the shear flow which we are going to impose. And this is our 3 direction. And this is the direction where our cylinders are aligned with a hexagon pattern. So we are looking at our object here. We're first looking at the 1-2 plane here, and the cylinders are aligned, and you can see that the reflection is in top and bottom, so our hexagon planes are like this. And the cylinders and the sample looked sideways are showing these reflections, and the cylinders going sideways are showing these reflections. And you can see that the reflections when looking at the sample from the top are a little more arced, so the order is not as severe as sideways where we have smaller arcs and the order is higher. That's the initial structure we are going to deform in a shearing experiment. This is shearing by 1.2 shear units, just a little bit of shearing. So the sample was heated up again to 140 degrees. The reflections are stronger here. I don't know whether this is just because we are shearing the sample a little bit, maybe mobilize the molecules, or maybe just heating it up again to 140 degrees and this little annealing. But I think it's the additional flow which improves the arcing somewhat. And so we still have cylinders like this. Sideways, they are aligned, or sideways, the cylinders are aligned like this too. Note that there's some intermediate structure coming in. So there's some regularity which gives us an additional reflection. The order wasn't perfect initially, so maybe some cylinders sticking out in their ordering very rapidly. And this intermediate order is even more drastic if we shear the sample by 2.8 shear units. The hexagons are still visible, not as strongly anymore. The intermediate structure is coming up here. And when this is from the side now, when looking on the top, you can see there's complete randomization. We are going from structure which had arcing this way to a structure which has arcing now this way. That's after many shear units. Somehow we already get alignment in this direction, and we will see from this type of alignment, we will see the arcing changing its direction. But I want to mention this intermediate structure also at, say, 2.8 shear units before moving on. We somehow get some ordering, and when looking at the microtome of that structure, now this is hardly visible at all. It shows that there's some alignment, and then there's an alignment by 90 degrees. So the vector has changed very rapidly for some region in the material. So it would be interesting to pick up those intermediate structures, learn more about this intermediate order. And of course, we speculate where this comes from. And it's, I don't think it's really too important at this point. OK, so at about 3 shear units, 2.8, the sample starts to randomize in its order. And close to 8 shear units, we already have the hexagon coming up. We have some reflections coming in. Those reflections are getting weaker and weaker. And then after 12 shear units, you will see the new structure coming in. Let me take this 12 shear unit and the initial order, and just to demonstrate how we go from the initial, from the 0 alignment here. This was, I don't know whether we can show those simultaneously. We go from this initial structure where cylinders are aligned like this, and when looking from the side, have this alignment, to a aligned structure where the cylinders are aligned now when you look at the sample head-on, and those arcs are pretty sharp, so the initial cylinder orientation has been lost completely. We're really going completely to this new orientation. And looking sideways, it's not as perfect, but somehow shearing produces a very nice order, and we see that transition. If we go beyond that, we have data of shearing to 20 shear units, and there the order deteriorates. We are randomizing the hexagon structure, and while still keeping the cylinder orientation for quite a while. So to sum up that this part here, I have some conclusions. For that strongly phase-separated system, we can say that the flow really introduces order at intermediate strains, and we are able to get have a global director for the entire sample. There are some defects in the material, but not only the director is showing order, the hexagon planes are also aligned, and the combination of those two are needed to describe the order in that system. Beyond that strain, the order deteriorates. The global director is maintained for some while, but we're getting a change in those hexagon planes and producing interfaces when scrambling the structure. And there are some intermediate transitions which we really would like to study also. Now, all those data are taken on a system which is strongly phase separated, far away from the coexistence temperature. At the end here, I want to show you a few data on a system which phase separates. We want to go through the phase separation and look at the effect of rheology, and in fact also want to structure the system while going through the phase separation temperature. And that's a new way of introducing order in that system. We can start in the phase separation, start in the single phase, if that's a typical coexistence temperature of the block copolymer. We start at high temperature, quench to lower temperature, introduce phase separation, and at the same time deform the material. And this way, as the structure develops, the grains are disturbed, or the grains are aligned immediately, and we're getting a very nice uniform single crystal structure when doing that. The material which allowed those experiments has been synthesized by Gronsky. It's a fairly monodisperse styrene, isoprene styrene, so it has a soft center block against styrene with its high glass transition temperatures. Is used here. It's close to 60,000 molecular weight, 24% styrene content, so we are talking about cylinders again. Tg is -70. The phase separation is fairly strong in that system, so we cannot say it's weakly phase separated. It is strongly phase separating, but phase separation needs time because of the long molecules needing long times to rearrange into a phase separated structure. The rheology of that system is, well, showing a very nice transition when we go from single phase to two phase or vice versa. Here's the modulus. In a heating experiment, here we have two phase, very high modulus, and then as the sample undergoes a transition to the single phase, the modulus drops. We are far above Tg. If you would continue that to go below Tg, there would be another rise here. So it's a melt. Both phases are molten in this system. Only due to phase separation, you have a drop in the modulus. You can see that the drop is very serious. It's several orders in magnitude as the sample homogenizes. The rheology can be seen most drastically at low frequencies. This is G prime as a function of frequency. At high frequency, nothing is seen. But you can see at 160, it's one phase. And when you go to lower and lower temperature. Actually, let's talk about melting. We start at 110, 120, 130. Not much is happening. But then at 140, it starts to go to single phase. And at 160, it's fairly uniform. So the transition can be seen in G prime. And somewhere, oh yeah, here I have G double prime. And again, also you see a strong transition at low frequencies. Very, very visible. We worked with, or we're still working on this with Hashimoto in Kyoto to do light scattering, in situ light scattering on those systems. So he will give us the corresponding information on the sample as they undergo phase transition. The protocol is something like this. We take a sample at up to high temperature, above the coexistence temperature, cool the sample down to, say, 125 degrees or 110 degrees, below the disordered transition, and expose it to large amplitude oscillatory shear. That's what LAOS stands for. So we're deforming the material in some large strains and hope that these strains promote order in one direction. And indeed, that's really what's happening. And we do that. So during the phase separation, we perform that experiment. The quenched sample is probed here, for instance, at one frequency. We just go from a single phase down, quench it to 125 to the phase separated structure, and look at G prime, G double prime. And you can see that the modulus needs long times to develop. This would be 10 to the 4 seconds here. So it's, we're talking really about hours. Down here it's about, what is it, 3 hours or so down here. The modulus develops very, very slowly. In contrast to that, and I don't have the figure here, it's interesting to look at Hashimoto's result. He finds that the sample phase separates very quickly. When he quenches to 125 degrees in a few seconds, he has fully phase separated structure. Somehow the structure phase separates into cylinders, cylindrical domains, but those cylinders are not connected to each other. They are individual units. And the connection, the healing of those cylinders needs a long time, and as those heal, the modulus is building up. And while the cylinders are healing, we are exposing the sample to large oscillatory shear. Just to show you how long it needs for the structure to build up, this is after 70 minutes. It's still a liquid here, G prime, G double prime going down. So it's a supercooled system, phase separated, as we know from Hashimoto's data, but not connected in a network yet. This is after about 160 minutes, the modulus went up. And after 11 hours here, the modulus here is fully developed. G prime is very high, G double prime. At 125 degrees, the modulus is high. So it's a nice solid behavior above the glass transition temperature of the styrene. But now I want to show you the X-ray patterns of that sample. You can see very high order. When you look at the cylinder sideways, the arcs are very sharp. And when looking at the sample in the direction of the cylinders, the arcs are also very sharp. And again, we have an alignment with the hexagon planes in the direction of the shear planes, are parallel to the shear planes. We are shearing the sample, And the shearing planes are really parallel to the hexagon planes of this order. The highest order we can achieve, and somewhere I had a micrograph, but that's also very, very, very uniform. So the interaction of a field with the self-ordering process of those phase-separating block copolymers is very interesting. At small strains, we affect the ordering in the positive way, saying we can enhance order, we can achieve global order as compared to local order in grains. If we overdo it, if we put too much deformation on the sample, we destroy the order, we take molecules out of this ordered domain structure and ask those molecules to reorganize at all times. We will have a fairly disordered structure, and that disordered structure is probably determining the processing, and often it determines the properties of as processed thermoplastic elastomer. So when you produce something with a thermoplastic elastomer, you most likely have the disordered structure and not the nice organization, which is shown in ideal experiments. And that concludes what I want to say about block copolymers. Definitely should do some more experiments on this system. Should learn more about interfaces produced in flow. Maybe some of you will continue that. But this concludes, actually, Becky, this is, and it's the last lecture on looking at a variety of blends and block copolymers and liquid crystals and different morphologies in rheology.